physics of thorium reactors. In this video, I'll explain how thorium nuclear reactors works. As always, this will be done with the help of simulations that capture the physics of nuclear reactors. Not only that, I'll also interview a professor of nuclear physics. But first, let's start with some advantages. The benefit of using thorium instead of conventional fuel like uranium. Thorium is much more abundant on Earth. It's also cheaper to mine. We don't need to enrich it as we do with natural uranium. Thorium is less suitable for making atomic bombs. It's not impossible though. We will have shorter-lived nuclear waste with thorium, i.e. cleaner waste. This video was sponsored by generous long-time supporters on patreon.com/hexeno, and generous one-time donations and generous support from Opera. Thank you very much everyone for helping me produce these videos. Implementing the simulation and disclaimer is the fourth video in the series Vision of Fission, so I won't spend too much time on basic nuclear physics and reactors this time. Anyways, as always, I'll do a very quick refresher. I'll visualize fissile uranium as a blue circle. In the simulation, I'll visualize a neutron as a black circle. When these particles touch, I'll set them to fission 100% of the time. I will depict the waste material as a single light gray circle. Control rods absorb neutrons and can move up and down. A normal nuclear water reactor will then look like this. This is a very simplified nuclear reactor of the conventional water reactors, which all industrial power producing nuclear reactors are today. This video will be about thorium only, so please, if you want to stay tuned for the molten salt reactors and the fast speed reactors, they will be coming on my channel. This video was sponsored by Opera Browser. Opera Browser has all of the modern features you need, like the floating music player. I can play or skip songs without interrupting my workflow. And speaking of atmosphere, I love that I can change the theme of my browser. The nicely integrated split screen makes it easy to multitask or compare data from multiple sources. When you have multiple tabs open, it can be easy to get lost. But with Opera's tab traces, the shade of the tab will indicate which one you recently visited. What's more, in Opera you can group together tabs in islands and expand and collapse them as needed. That's very useful for organizing clusters of tabs. The last feature I would like to show you is the built-in AI tool Area. You can quickly access Area's command line with the simple shortcut Ctrl+/ and ask anything. It can also generate images. And lastly, it can detect what's on images. That's some of the smart features of Opera. If you want to give it a go, download it now, the link is in the description. How thorium works. Normally, reactor uses uranium-235 to fission and produce power. So can we just do that with thorium instead of uranium? The answer is sadly no. Thorium does not have the property of being fissile, but we can change the thorium into an element that is fissile. How? Let's see this on the nuclei chart here, with all of the known nuclei. The starting material is thorium, the isotope thorium-232. If we hit thorium-232 with a neutron, it will transmute into thorium-233. If we then wait a bit, it will then beta decay to protactinium-233. Beta decay is a process where a neutron decays into a proton. Then it will beta decay once again and become uranium-233. This nucleon is fissile, just like uranium-235, and will absolutely work as fuel in a nuclear reactor. Let's replay this nuclear chart again, but this time show how much time it takes for the decays. First, absorbing a neutron does not have any half-life, it's pretty much instant. Going from thorium to protactinium have a half-life of only 22 minutes. This is so short of a time span, I will ignore this specific step soon. But going from protactinium to the fissile uranium has a half-life of 27 days. Let's introduce some colors for our animation. Let's paint the starting thorium tomato colored. Then we ignore thorium-233 and we pretend that the next element is protactinium-233. I'll color it dark gray. Finally, I'll depict uranium-233 as blue. Hey, isn't that the same color that you used for uranium-235 and for xenon in the previous videos? Yeah, it is, and that's because they will play the exact same role. Good eye. So, To conclude on this part, while the thorium-232 isn't the actual isotope splitting, it can be transmuted, i.e. changed into a fissile material. Materials that have this property are said to be fertile, and reactors that produce more fuel than they consume are breeding reactors.
So it might sound like thorium is the best thing ever, but why don't we see it everywhere then? Let's discuss some issues. And the first one, the neutron economy. So what I showed you before will correspond to this in my simulation. We start with thorium, send in a neutron, we get protactinium, then we wait, and we finally get the fissile uranium. We then send in a neutron, and finally we get the fission. I'm trying to show the same process you saw earlier on the nuclei chart. You can see we use 2 neutrons and only get out 3 neutrons of the fission. So all breeder reactors need a minimum of 2 neutrons released per fission. One to produce fissile nucleus from fertile nucleus, and a neutron to induce the fission. So I hope you can see the low yield of neutrons can be a major challenge, since we need to take into account for neutrons lost due to leakages, captures of other non-fissile nuclei. That's a major challenge for effective thorium breeder reactors. And here comes another challenge, protactinium issue.
In a perfect world, without any issues, we'll just take our thorium and give each a neutron. Then we wait while the protactinium exponentially decays to the fissile material. Of course, we don't live in a perfect world. What are the issues then? Let's convert this to thorium again. I want to show you an issue with the protactinium. To show this, I'm going to continually blast in a lot of neutrons from the right, but from the left, I will only send in neutrons in waves. What I want to show you is, to effectively utilize thorium for breeding, you can't just blast it with neutrons, because then the chance of protactinium absorbing the neutron is just too high before it has any time to decay naturally. Because the chance for protactinium to absorb the neutron is simply too high. As shown on the left instead, you must give the nuclei some time to rest, such that the protactinium can beta decay into the fissile uranium. One example to effectively utilize the thorium fuel is by inserting groups of thorium into an already running reactor, with the goal of taking it out later for the protactinium to rest and convert into uranium.
Let's run the reactor for some time and pull up the thorium groups. After some time, thorium has changed into protactinium, some of it had changed into uranium, some of it has changed into uranium and already fissioned, and some of it didn't get absorbed by any neutrons. So you can see from this group we pulled off the reactor to produce our breed fission fuel. We now need to chemically reprocess and get all the fission fuel out. First of all, this is dangerous because there are radioactive isotopes. It's also expensive, and lastly, it also takes some time because of the protactinium's long half-life of 27 days.
A strategy is to irradiate some thorium and let it sit for a whole year.
And then finally, you can pull out the uranium. And all of this work of breeding just to avoid enriching uranium, which is by the way cheaper. Blanket in light water reactor. There exist many types and complicated reactor types that are currently being developed and researched with the goal of running uranium-233 and thorium. However, if you forget all of these fancy reactors and the breeding fact, then there is a really fascinating and promising fact about thorium fuel. Good old conventional reactors running today have the potential for thorium to be used with them,
without any major modifications.
Simply by implementing the so-called seed blanket reactor design. In a seed blanket reactor, conventional uranium-335 is used as fuel, inside as a supplier of neutrons. On the outside, the blanket is the consumer of neutrons, and here you will simply put in thorium. This time we aren't hoping of breeding or producing more fuel than we used. Instead, we are just modifying already existing conventional reactors to boost them to reap some of the thorium benefits.
Why are the products cleaner with thorium? In my simulation, I've shown every time the fissile uranium-233 interacts with the neutron, it has undergone fission. This is actually not correct. 1 out of 12 times, or 8% of the time, it will just eat the neutron and transmute into uranium-234. Compare that number to the conventional reactor fuel of uranium-235 instead. This fuel is actually less efficient and will absorb the neutron instead of fissioning about 1 out of 6 times, or 16% of the time. That's a big difference, because when the fissile material chooses to absorb and transmute instead of fissioning, that's how the terrible, problematic and long-lived nuclear waste is built up in a nuclear reactor. called the transuranic elements. That's elements heavier than 92 protons. Because the nuclei did not split, now it will continue absorbing neutrons and become heavier and become this problematic waste. The point is here, the thorium does this much less than conventional fuel. This is the reason conventional nuclear reactor waste is difficult to deal with. A huge plus for thorium. Although a known drawback for thorium fuel is we get a lot more strong emitting waste, but not long-lived. I just want to quickly mention we can pretty much get all of the same benefits as thorium by breeding with uranium-238 in a fast fission reactor, i.e. non-thermal. But thorium is the only element that can breed and run fission with thermal neutrons, which gives other advantages and the disadvantages. But fast fission is a story for another video.
Here at Aarhus University with Professor Hans Fynbo, who taught me nuclear physics and particle physics back in the days. So I know for a fact that he is extremely knowledgeable, but also really interesting to listen to. So thanks a lot for being here today.
Sure.
Or actually we are in your office, but thanks for being on the channel. I really appreciate that.
Pleasure.
If you could snap your fingers, then everyone in the world would understand one aspect of nuclear energy or nuclear physics. Do you have any idea what it would be?
How dense the energy is, the nuclear energy is, how little material you need to create a lot of energy.
Yeah.
And therefore also how little spent nuclear fuel is in amount, in kilograms of volume, relative to the amount of energy that is created.
Are there any research or projects on thorium you find particularly promising?
There are a number of small test reactors sort of building on from what was done in the 1960s with the molten salt reactor experiment.
Yeah.
So in the US, China, Russia, and Europe is also coming along now. So many people will have heard about various startup companies.
Yeah.
I think those are very interesting. These people are interested in creating a cheap, scalable energy source that can get rid of this fossil fuel.
What do you think are the biggest technology breakthroughs needed for making thorium reactors competitive?
I don't know whether you can call it technological. We need to have a scheme of getting these devices approved by authorities. And so the full approval machinery. I mean, there's not really so much research questions that are in terms of fundamental properties of the isotope. I mean, how the neutrons are absorbed and some of the cross sections, as we call them. I think they're pretty well measured.
Yeah.
Maybe there's some material properties of what materials one can use for the containers. There's a technical challenge of how to make the geometry and the material choices so that what you call the neutron economy is as high as possible, so as few neutrons as possible escape into the environment or are absorbed by infrastructure inside the reactor.
Yeah.
So that the more neutrons that survive, the more you can use the neutrons to make new fuel in the breeder reactor.
Do you see any future application for just boosting normal water reactors, live water reactors with thorium?
I don't think that the potential there is very large. Of course, if you have some other device where you can make the thorium into uranium, and then you can put that into traditional reactors, like water reactors.
Yeah.
If you have like a system of reactors going where you have some that can make the thorium into uranium, and then you can use the other type of reactors to put that in as traditional fuel. When you use the uranium that has come from thorium, rather than the uranium that has come from natural sources, then you have a lighter isotope, the 233 rather than 235 or 238, and that has the advantage. I mean, you might think that that's a small difference, 233 versus 235, but that means that you create fewer of those actinides, as we call them, americium, curium, plutonium. And they are the ones that have the longest lifetimes, and therefore creates the need for storing the spent fuel for the longest time if you don't do anything with them. If you just removed all those actinides, then the time where the spent fuel is reactive is more of the order of hundreds of years rather than 10,000s of years.
Yeah. Would you also say that it would be smart to focus the chemical separation of protactinium?
Then you have to have it in a configuration where you can take it out. Sort of, in a normal light water reactor, you don't open all the time. Yeah. So you have to, like, every 1.5 years or 2 years or something like that, because you have this pressure tank. It's not an easy exercise to to open that and take out the fuel and so on. So there is an issue of how often should you do this. I mean, you cannot wait a year and a half, because then, I mean, the protactinium can also absorb neutrons, and then you might generate some other isotopes than the one that you're actually interested in.
Yeah.
You would like to have the thorium-232 become uranium-233. And there are some other uranium isotopes that can be also produced that you would not like to the same degree. I think it's uranium-232 can be produced by a certain type of reaction. It emits a gamma ray with high energy that creates problems for handling this material.
Yeah, I've seen some numbers. 100% sure it's not correct, actually, but I would love to know how you think that number is calculated, because I found multiple sources saying that 1 ton of thorium is equivalent to 200 tons of uranium.
And that depends to a large degree on what technology you are then using to extract that energy. So that number that you quote probably comes from, if you look at uranium, it's only 0.7% of natural uranium that is the fissile isotope 235 uranium.
Yeah.
So whereas if you go to thorium, then actually thorium, there's only one isotope that we find in nature, 232, which is not in itself fissile. You have to do something to it, which I think we'll come back to maybe.
Yeah, exactly.
So that ratio is perhaps not the most correct, I would say, because you can also make the non-fissile isotope of uranium, the most abundant one, 238. You can also make that into a fissile element, plutonium, 239 mainly. So in that sense, that comparison is not maybe the most fair.
Yeah, all right, the most fair.
I realize this video is just me blasting tons of thorium facts, but I hope you got these takeaway points here. Thorium-232 is a fertile isotope that can be converted into fissile uranium-233. With a high enough neutron economy, thorium can make more fissile fuel than it uses. The middle step, protactinium-233, has a relatively long decay time, which complicates fuel breeding. Conventional light water reactors could in theory use thorium right away with minimal modifications, allowing for partial benefits of the thorium fuel cycle. Uranium-233 produces less long-lived nuclear waste compared to conventional uranium or plutonium fuel.
So why don't we use thorium? It's a technology almost as old as fission itself. It has already been proven to work. Thorium is a very interesting and promising fuel, but it needs more research and it needs to become cheaper and safer, specifically cheaper and safer than using the good old tried and tested uranium-235. Still, the thorium fuel presents a promising and capable technology for the future of green energy.